So we're beginning chapter 6.1, which talks about composition of functions. Let me see if I can hide. So we need a definition of a composition of function. If we're given two functions, f and g, the composite function denoted by f with a little symbol in the middle, g. This is read as f composed of g is defined by f composed of g x is the f function substituted with the g function. The domain, and this is important, the domain of f composed of g is the set of all numbers x in the domain of g for which g of x, the entire g function, is in the domain of f. Just a quick illustration of the generic form of finding a domain. If I'm given, say, two functions, find the domain of f composed of gx where f of x might be equal to, let's say, 5 over x minus 1, and g of x must equal to 4 over 3x minus 2. So notice that first, the domain of g of x cannot include, if we set the denominator equal to 0, cannot include 2 over 3. And the domain of f cannot include +1. But they're strictly asking about f composed of g. So we know immediately that x is equal to 2/3 cannot be in the domain. Now what this definition of domain is saying for this particular case, f composed of g, is that we take that 4/3x minus 1 and set it equal to the number that is excluded in the domain of f. And solving this, we would get 4 is equal to, sorry, this is 2, right? 4 is equal to 3x minus 2. So x is equal to 2. So the domain of f composed of g is all numbers except for 2/3, which is the domain of g, and then the number of the substituted value into the f function from the set equal to the excluded value of the f function, since we're doing substitution as a matter of cause. Also want to make sure that we know how to evaluate functions. So I'm just going to do a quick example here. Suppose, say, f of x equals to 5x minus 1 and g of x is equal to x squared. Find a f composed of g substituted with 1. So this is solved by rewriting this as f substituted with g substituted with 1. So this is f, is it 3? Yes, because gx is equal to 3x squared, and if we substituted 1 in here, we get 3. So now we're going to go ahead and substitute the f function with 3. So this is 5 times 3 minus 1, which is equal to 14. We may also be asked to find the g function substituted with f, let's say with 1 also. So this is, if we follow the process here, this is the g function substituted with the f function, which is g. So f of x is equal to 5x minus 1. f1 is equal to 4. So g substituted with 4 is 3 times 4 squared, which is equal to 48. If we're asked to substitute the f function with itself and substitute a value, let's say f substituted with f, substituted with, say, -2. What we have happening here is this is the f function substituted with f -2. And I don't think I mentioned that here. Yeah, this is, sorry, f4. Need to fix this. F substituted with 1. So this is the f function substituted with 2, which is f. And we're going to find out -2. So f -2. If we're substituting, this is 5 minus 2 minus 1, which is -11. I'm substituting in the original f function right there. So we have to find f -11. So again, go back to the original function and substitute 11 in it. 5 times -11 minus 1, which is 5 11 is 55, minus 1, -56. We can perhaps take one more case of this. If we're finding the g function composed of the g function, say substituted with the same -2. So this is the g function substituted with the g function with -2 in it. So we need to find out what g -2 is, and that means we're substituting into the original function. The original function is 3x squared, so 3 -2 squared, which is positive 12. So this is g substituted with 12, and this is 12, 3 times 12 squared, which is 432. Now I want to go through a few problems of actually composing one function of another. If f of x equals to 5x plus 3 and g of x is equal to 3, determine the following compositions and state the domain. So this is 3x. So part A is asking about f composed of g. Now, before we do anything, we notice that for f of x is equal to 5x plus 3, the domain is x, all real numbers. It's a linear function. And for g of x is equal to 3x, the domain is also all real numbers. So to go ahead and solve here, we're going to take the original function, which is 5x plus 3, 5, open parenthesis here, for x plus 3. And into that space, we're substituting the g function, which is 3x. To give us 15x plus 3. Now the g function, the domain of the g function was all real numbers, and the domain of f composed of g is also all real numbers, since it's a linear function also. So the domain is still all real numbers. Part B is asking about g composed of f. So we're going to start out with the g function, which is 3x, and into the x part we substitute the original f function, which is 5x plus 3, and distribute to give 15x plus 9. The domain of the f function is all real numbers, and the domain of the resulting function, composed function, is also linear, so also all real numbers. Okay. Let's look at the f function composed of the f function. So in this case, I'm taking the f function, which is 5x plus 3, and in place of x, leaving a parenthesis. And into that parenthesis, I'm going to substitute 5x plus 3. I'm substituting the f function into itself. Distributing, I have 25x, 5 threes are 15, plus 3 is 18. Domain, as you can see, remains all real numbers. Then we're looking at the g function composed of itself, which is, the g function is 3x, so into x place we will substitute 3x to give 9x, which is also a linear function. Domain is all x, x all real numbers. Let's look at a few more examples. Let's go ahead and take perhaps a this is given f of x is equal to the square function x squared, and g of x equals to the square function up 6 places. Determine the following compositions and domain. Before we do anything, we want to notice that for f of x equals to x squared, this is a quadratic function, so the domain is all real numbers. The domain is all real numbers. And g of x is also a quadratic function. So the domain is still all real numbers. Now we're going to go ahead and go through the process of finding compositions. So F composed of G means we're substituting the G function into the X function, and in this case X is yes, the G function, the F function substituted it into it. The G function substituted into the F function, so the F function is X squared. So we're going to leave parentheses, and into this we're going to substitute the G function, which is X squared plus 6. FOIL that out, and we get x to the 4th power 6x squared plus 6x squared, which is 12x squared plus 36. This is a polynomial, so the domain, and then we consider the G function. The domain of the G function is all real numbers, and then the polynomial here is all real numbers. So the domain is all real numbers still. And FYI, we're dealing with polynomials here, so the domain is not a combination of, say, a polynomial and a rational function, so the domain will remain all real numbers for every single case. No worries, okay? G composed of F, we would take the G function, which is x squared plus 6, and into the G function we substitute the F function, which is x squared, to give x to the 4th power plus 6. Polynomial, domain, all real numbers. This is part B, not D. Let's consider the G function, the F function composed of the F function. So this is simply x squared substituted with x squared, which is x to the 4th power. Domain, all real numbers. And the G function composed of itself, which is the G function here is x squared plus 6. So now we've already worked out x squared plus 6, which is in part A. So this is x to the 4th power plus 12x squared plus 36 plus 6. And resulting function is x to the 4th power plus 12x squared plus 42, which is still a polynomial, and we know that the domain of all polynomials is all real numbers, and the domain of the G function is also all real numbers, so not a big deal to worry about. I want to go ahead and look at a couple of rational function examples. So given f of x is equal to 2 over x minus 5, and g of x is equal to 1 over x. Now notice the domain here, x cannot equal to 5. That would make the denominator 0. And in this case, x cannot equal to 0. So we want to go through the process here and look at a variety of compositions. F composed of G is the F function. We're going to leave x blank, and in place of x, we're going to substitute the G function, which is 1 over x. So this is a complex fraction, meaning we have to multiply everything by x to clear that fraction, 1 over x. And this is 2x over 1 minus 5x. Now, things to consider. We know that this function, because it's composed of g, the domain cannot include 0. All x. And we know that, first of all, that it cannot include 0 because the g function has a domain exclusion of 0. And then if we set that denominator equal to 0, we see x is equal to 1 over 5, which is the number that would make the denominator 0. So x cannot equal to 1 over 5. Now let's look at the g function composed of the f function. So the g function is 1 over x. In place of x, we're putting the entire g function, which is 2 over x minus 5. So use the keep, flip, and change rule here. Keep the numerator, flip the denominator, and change the sign to multiply. So this becomes 1 x minus 5 over 2. The resulting function then is x minus 5 over 2, which, as you can probably tell, is a linear function. This is half x minus 5 over 2. Domain. So this function is composed of the f function this time. So x cannot equal to that domain, that 5 that's not to be included in the domain of the x function. And then the resulting function is a linear function, which is all real numbers. So we don't have any other exclusions to add to the domain. There's no other number that would make the denominator 0. If you look at the denominator here, it's 2, and nothing can be substituted in here to make the denominator 0. Next, we're looking at the f function composed of itself, which is 2 over x minus 5. So in place of x, we're writing the f function, which is 2 over x minus 5. And we have a complex fraction here, so 2x minus 5 over 2x minus 5 times x minus 5 minus 5 times x minus 5. Remember to multiply all of the terms by the LCD. So this is 2x minus 10 over 2 minus 5x plus 25, which simplifies to 2x minus 10 over, what is that, 25 into 27 minus 5x. Now, remember that for the f function, we cannot have 5 in the domain. So this is really important here. X cannot include 5. And then if we set the denominator equal to 0, we get x is equal to 27 over 5, which is the number that would make this reciprocal here equal to 0. So we also have to put 27 over 5 as one of the numbers that cannot be included in the domain of all real numbers. And then finally, we're going to look at the g function composed of itself, which is 1 over x. And then in the place of 1 over x, we substitute x. So again, the keep flip change rule here, which is x. So the resulting function is simply a linear function. Domain, although this is a linear function, we still have to consider that the domain of the g function, cannot include 0. So, and this is the g composed of the g function, so x cannot equal to 0 would be our domain here. Next, I want to look at sort of finding the components of the composite function. Finding the components of a composite function. That is, undoing the composite function to see what we have. Problems like this may be of the form, say, find functions f and g such that f composed of g is equal to a function designated as h when say the h function is given as um 3x squared minus 5, let's say to the 19th power. So this function h raises the expression 3x squared minus 5 to the power 19. A natural way then to decompose h is to raise the function g of x 3x squared to the power 21. In other words, let function f equal to x to the power 19 and function g equal to 3x squared minus 5. So function f composed of function g is f substituted with the entire function g, which is, f substituted with 3x squared minus 5. So we're going to go to that function, the original function, and say that is 3x squared minus 5 to the 19 power. So the component parts that we're looking for are f of x is equal to x to the 19 power, and g of x is equal to 3x squared minus 5. Two more examples here. So f composed of g is equal to h when h of x is, say, 1 over x plus 3. So here h is the reciprocal of g of x is equal to x plus 3. So let f of x equals to 1 over x and g of x equal to x plus 3. Then f composed of gx is equal to the f function substituted with the g function, which is f substituted with x plus 3, which is 1 over x plus 3, which is the h function. So solution then is f of x is equal to 1 over x and g of x is equal to x plus 3. One last example. So assume that f is composed of g is equal to hx. So here, and we're told that hx is, hx is equal to the square root of x squared plus 20. So here h is the square root of g of x, which is in this case x squared plus 20. So let f of x equal to square root of x and g of x equal to x squared plus 20. So f composed of g is f substituted with the g function, which is f substituted with x squared plus 20, which is equal to the square root of x squared plus 20, which is the h function. So our component functions, f of x is square root of x, square root of x, and g of x is x squared plus 20. Now I want to, and normally I would have you try this problem in class, but I want to do this separately. So f of x is equal to pardon me, I have the wrong example here. Let me pause this with. Okay, so here we go. F of x is, say, the square root of x. This is the challenge problem. And g of x, let's take g of x as a simple linear function. So the domain for the square root function is all x, such that x is greater than or equal to 0. And the domain of the linear function is all real numbers. And let's look at a few compositions, maybe one or two compositions here, and see if we can figure out how to not only to compute the composite function, but how to find the domain. So this is f composed of gx, which we're going to substitute the f function with x minus 2. And so this is simply the square root of x minus 2. Now the domain of for the square root is all input that makes x minus 2 non-negative. That is all x such that x minus 2 is greater than 0. So keep this in mind. The domain of f of x is equal to, sorry, the domain of f of x equal to, I've got the wording here, of the square root of x minus 2. We figure that domain by setting the part under the square root sign is equal to 0, and we said that x must be greater than or equal to 2. Now, consider this in relation to the domain of the original function. The g function said this was all real numbers. But the restriction here is that the domain must be greater than or equal to 2. So the domain of f composed of g, x, is all x such that x is greater than or equal to 2. And we're just going to consider one other case, g of f x. So again, this is a g function substituted with the f function, which is in place of x. In place of x, we're putting the square root of x. Okay, in that place, we're putting the square root of x. So the resulting function is the square root of x minus 2. So now we have to consider domain here. The domain for this is all the input that makes the square root defined. Domain is all inputs that make the square root of x defined. So x has to be greater than or equal to 0. And if we consider the original function, domain is if x is greater than or equal to 0. And this function here, this function here, what's happening here? Here we go. Since the x is underneath the square root sign, x still has to be greater than or equal to 0. So the domain of g composed of f x is all x greater than or equal to 0.